In this talk, I will present our recent paper on client-server sessions in linear logic in collaboration with Alex Cavos and Lars Bjerkdal. First, let me say something about the background. So concurrency is ubiquitous in modern software, and there have been many approaches to modeling concurrency like these. Now, without diving into details, these models, while serves the purposes of modeling different styles of concurrency, don't give fundamental logical meanings to programs. This is in sharp contrast with functional programming, where we have the notion of Curry-Howell correspondence or proposition as types that establish the tight mapping between programs and proofs. It's not only elegant but also useful. So naturally, in the early 1990s, Samson Abramsky asked if there is something similar for concurrency, and the answer is widely believed to be a correspondence between some kind of process calculus and proofs in classical linear logic. And this program is commonly known as proofs as processes. Early attempts include Abramsky, Berlin, and Scott, who maps CLL proofs to a variant of pipe processes. However, under their mapping, processes can only send and receive pairs, which seems not general enough. In 2010s, the problem was solved by Kyrus and Fanning for intuitionistic linear logic, and later adapted to CLL by Wadler. Finally, Koch et al. Borrowed ideas from hypersequent, and we now have a tight correspondence between a variant of pi calculus and hypersequent CLL. Now, a concrete reason of why we want such a correspondence is that the properties of CLL would apply to the corresponding process calculus automatically, such as deadlock freedom, session fidelity, and live lock freedom. Now, here's the bad news. All these systems have remarkably poor expressivity. They lack some common concurrency phenomenon such as races. And there are many works on fixing that, and our paper focused on adding client-server sessions to CLL with a degree of races and non-determinism. First, let's look at Wadler's classical process, or CP in short, that our system is based on. It's a session-typed pi calculus. The types are formulas in CLL, and programs corresponds to proofs in CLL, just as one would expect. We have the multiplicative fragment, including sending and receiving end-of-session signals, sending and receiving channels along channels. We also have the additive fragment, including making and accept choices. We also have the exponential fragment, including the question mark and the band, which we will dive in later. The duality is defined for session types, and dual sessions can talk to each other, and the duality is apparently an involution. Next, we look at the typing rules of CP. Typing judgment will be of this shape, and it means that process P will communicate along channel X according to protocol A or type A. If I have two processes with dual channels, I can connect the channels and get a process. If I can also create a forwarding process out of thin air that exposes two dual channels. If I have a process that communicates along two channels, I can make a process that communicates on only one channel, and the new process will receive the second channel along the first channel, and the type will reflect that. And it's similar for sending channels. There is, however, a notable difference, which is that the former rule constructs from a single process P, but this rule constructs from two separate processes, P and Q. After the second channel is outputted along the first channel, the two processes can continue in parallel. So in some sense, we can say that the former is connected concurrency, while the latter is disjoint concurrency. Following are the three additive fragment rules. If I have a process P that behaves as A, I can make a process that selects A out of A and B and then behave as A, which is P. I can, similar for B, and if I have two processes, each behaving A and B, then I can make a process that accepts the choice of A or B and then behave as such. We now turn our eyes to exponentials, where we improve over previous works. Here are the rules, and let's go through them in Wadler's interpretation. So the gist is that ban means server and question mark means client. The weakening rule represents constructing an empty client pool from nothing. The dereliction rule is constructing a singleton client pool from only one client. The contraction rule is merging two client pools into one client pool. Promotion is producing a replicative server from a process that will be replicated. And yes, so that sounds all right until we have to construct concrete examples. Suppose I have two processes or two clients P and Q, each exposing an A channel, which is the client protocol, and the question is how to combine them into a pool. Well, you can have this very straightforward derivation, at the end of which we have the question of A, which is a client pool of A. But one notable thing is that we used a mix rule, which is not standard in classical linear logic. And it's similar for creating an empty client pool from nothing. We will require a mixed zero rule, which is also not standard in linear logic. And indeed, that's what Wadler and many others did to accommodate client pool using exponentials. But the story doesn't stop here. Gerard wavers on whether they should be included in CLL because they are problematic. In short, mix degenerated the multiplicative fragment of linear logic, and in particular, if we look at the mixed zero rule, it allows you to derive contradiction from the unit. This is obviously bad from a logical point of view. So using exponentials to represent client server doesn't work out, and we are going to find out why with the help of fixed point. We often think of ban A as infinite supply of A and question A as consumption of that. It is therefore very natural to try to encode them using fixed point. Indeed, this encoding gives a logical equivalence. Now, if we flip the multiplicative connectives in the encoding and get another set of modalities, which we will call co-exponentials, and the question is, what's the difference between these two kinds of modalities, and is co-exponentials useful at all? So let's compare the two sets of modalities. In the encoding of exponentials, a server is either nothing, a single A, or two subservers connected by a tensor. Now remember that, as we mentioned, tensor represents disjoint components, so there can be no communication between the two subservers, hence it can be a stateful server. In contrast, in the encoding of co-exponentials, we have the two subservers connected by par, which represent connective concurrency. There can therefore be communication between the two subservers, which forms into a stateful server. So it seems that co-exponentials are more suitable than the exponentials to represent client server. Indeed, our slogan is K means client and Claro means server. We derive some rules from the fixed point to make it more usable, and to introduce non-determinism, we quotient some permutations such that the order of which clients are added to the pools does not matter. Finally, here is our system, client-server linear logic. It's based on this Popple 2019 paper and uses hyperenvironment to decompose C terms of classical processes. Tensor and cut rule are copied from the Popple 2019 paper. The K weakening, the K absorption, and the clutter rule are essentially identical to the three rules in the previous slides, but with term assignment. Our system comes with a reaction relation that satisfies progress and preservation. Now here is an example of what can be done in our system. Cas is a powerful and common concurrency primitive, formally defined as such. Here we consider Cas of a single bit for simplicity. We can use server to represent a CAS-capable register, and client pool to represent threads racing to perform a CAS. And the client protocol will be defined as sending expected value, sending desired value, receiving the result of the CAS operation, and ending the session. And of course, the server protocol is the dual of that. At some point, we realized that CSLL is a very low-level language and it's tedious to write programs in it. We therefore made a high-level language CSGV, which is linear functional programming with session types and client servers based on Waddler's GV. In CSGV, we are able to write more examples. We define the server of data structure to which each client has atomic access. We define the choice process that returns 0 or 1 randomly. We implemented fork join parallelism. Finally, we implemented Kinney's beauty contest, where each client votes for a candidate and hear back the result in a single session. These examples demonstrate that our system allows some degree of sharing and non-determinism while being deadlock-free. In the related works, all previous CLL-based approaches had to use mix, except this paper by Kalkamaris and Waddler, where they use bounded linear logic to model server and client. However, in that system, a server can only serve an exact number of clients, which is quite restricted. There are other two approaches, namely multi-party session types, where multiple parties of each rule interact with each other according to a global protocol. This is, of course, different to our system where there are only two rules, namely server and client, and the number of clients is variable. There is also Kobayashi's who added type system to pi calculus in pursuit of good properties. They, however, didn't aim for any connection to linear logic. Finally, our co-exponential rules are very similar to some of the exponential rules in differential linear logic, but we are not sure about the connection. There are several future topics to look into. First, our Clever rule derived from fixed point is apparently a generalized version of a supposed co-promotion rule, which is supposed to be symmetric to the promotion rule and still be useful for logic. We attempted to weaken it or specialize it to match the promotion rule, but encountered some issues in co-elimination. In particular, it's some commuting conversion that wouldn't work. Another future topic is to develop a logical relation toolkit for CSLL or CLL in general. And this could be useful for proving, for example, strong normalization for the systems. So there are many syntactical proofs of termination of CLL, but as far as I know, there hasn't been a logical relation proof.
Hi, I'm Nikos Vasilakis, and together with Shivam Handa, Konstantinos Kallas, and Martin Reinhardt, we're bringing to you a data flow model for parallel Unix pipelines. All of the work you'll be seeing today in this video and corresponding paper is open sourced and available for download at beanpad.sh. Shell scripts are used pervasively. They're used for orchestration and deployment of modern container workloads, for succinct and concise data processing, and for other automation and configuration tasks. For example, here's a data processing script calculating average temperatures across the US over a 5-year period. Here's another script, a fragment from Pash's cross-platform installation configuration scripts. Here's a fragment of a container deployment script. Here's another script, and here's another script, all of which are supposed to convince you about the ubiquity of shell scripts. A particularly common programming pattern in shell scripting is what's commonly referred to as Unix pipelines. Pipelines contain or chain together individual stages using a composition primitive known as the Unix pipe. Individual commands can be written in any programming language and focus primarily on processing their inputs and emitting outputs, while the Unix kernel takes care of synchronization and inter-process communication under the hood. This language agnosticism is powerful because it allows composing stages developed in any language, ranging from Python to Ruby to C++ binaries and other shell scripts. But it's also challenging because there is no unified program analysis that can be applied to all these commands to extract useful properties. That is, from the point of view of the shell, these commands operate as black boxes. To better understand Unix pipelines, consider a classic spell checking pipeline from the 1980s, the precursor to the Unix and Linux spell program, slightly modified for modern workloads. The first command streams two markdown files into a pipeline that first converts characters in the stream into lowercase, then removes punctuation and emits one word per line, then sorts the stream in alphabetical order, then removes duplicate words, and finally filters out words from a dictionary file. The second pipeline counts the resulting lines, reporting the number of misspelled words to the user. But what if instead of two small input files, we had a half a terabyte of input data? To accelerate the computation, we would want to leverage data parallelism. First, split the half a terabyte input data, then apply the computation in parallel across partial inputs, and finally, cleverly combine the results to produce the correct outputs. To achieve such parallelism, however, we're left with only a few alternatives. One alternative would be to use parallelism flags, such as -p for GNU sort. This alternative doesn't go a long way, as first, it only works for some commands, specifically ones whose developers have explicitly provided parallel operation, but not other commands. And two, does not compose across commands or pipeline stages. Another alternative would be to rewrite the entire pipeline in a new programming language that supports parallelism. That alternative would require too much effort and forego all the benefits of language agnostic and succinct program composition, which is the hallmark of the Unix design. Yet another option, and likely our best bet, would be to apply a tool such as GNU Parallel. Unfortunately, GNU Parallel only supports embarrassingly parallel shell scripts, require manual effort from its users to discover and map divide and conquer parallelism. It is also agnostic to pipeline semantics, and its application results in script changes, which, as we'll see, leads to ugly and unmaintainable scripts. Take a look at only the first pipeline of the spell checking script. Oops. We believe we deserve better, and in this paper, we propose a parallelizing shell-to-shell compiler that builds on a precise data flow model of shell pipelines as its centerpiece. We formalize this data flow model and associated translations from shell scripts to the model, as well as from the model back to parallel shell scripts. We also formalize and prove the parallelizing transformations applied within this model and implement everything as an end-to-end shell-to-shell parallelizing compiler that takes its shell script and produces a parallel version of it. To get an idea of our compiler, we will apply it to the spell check script. Note that in this talk, we hear more about the intuition and insights behind the contributions, but full details can always be found in the paper. The first thing that the compiler does is to convert the script to an abstract syntax tree and then identify data flow regions. Data flow regions in pink and purple over here are script fragments comprised only of some command composition constructs that may allow parallel execution depending on the commands used in these regions, but not other composition constructs that operate as sync barriers. For example, data flow regions can contain the pipe character, but cannot contain the semicolon character, which denotes sequential composition. The compiler then converts these regions to an intermediate representation and code it as a data flow graph. Nodes in this graph are Unix commands, and edges are channels connecting these commands, which in Unix correspond to pipes or FIFOs for inter-process communication. The compiler then applies parallelizing transformations. For now, we'll be focusing only on the first data flow graph. It first parallelizes individual commands, adding nodes for splitting inputs and merging partial outputs, as in the tr example command here, and then starts pushing parallelism further across the data flow graph. First, to the two TRs, and then towards sort and other commands in the data flow graph. Finally, the compiler translates the parallel data flow graph back into a shell script by encoding nodes as concurrently executing commands and edges as FIFOs, or also called named pipes. It leverages explicit synchronization primitives provided by the shell to guide the parallel execution of the parallel script. As we will see, this iterative parallelization process can lead to significant speedups for a variety of scripts. But before we see that, how is this process even possible when we explicitly stated at the beginning of the talk that Unix commands are black boxes? Well, part of the insight here is provided by recent proposals such as PASH and POSH, which identified command annotations as a way to communicate partial specifications of individual black box command behavior. For example, these annotations can be used to express whether a command is pure, that is, whether it reads and writes only to files and streams, or whether it performs additional side effects. We leverage this insight to change our perspective. Rather than operating at the script as black box level, we can zoom in and operate at the script as a composition of black box commands level. This change of perspective allows us to create a precise enough data flow graph model of shell pipelines, which can then be manipulated using transformations that expose parallelism in the data flow graph, as shown in the example earlier. A crucial point of this data flow model is that it captures the order in which commands read their inputs. This order needs to be preserved when parallelizing and is unlike other data flow models such as MapReduce, where commands are commutative and associative or independent with respect to some key. Consider this order-aware data flow example. cat reads first from F1 and then from F2. This order awareness also distinguishes between 1, configuration, and 2, streaming inputs. Consider this other order-aware data flow example. grep is configured by first reading the dictionary file and then reading its streaming input from the output of unique. Note that this information is enough to enable correct parallelizing transformations. Specifically, Our compiler does not care about commands themselves and still views them as black boxes that just happen to satisfy certain properties. For example, one such property is that some commands are amenable to divide and conquer parallelism. The compiler transformations then manipulate such compositions of black box commands to enable parallelism as shown in the example earlier. This order awareness makes the data flow model expressive enough to describe widely used data flow fragments of the shell, which is important for the shell to the DFG translation, the data flow graph, but which in turn can be implemented in the shell, which is also important for the data flow graph to shell transformation. As a result, after the compiler has applied transformations to parallelize the composition of black box commands, it simply transforms the data flow graph back to the parallel shell script, which can in turn be executed by a standard interpreter. We incorporate our work in Pash, an open source parallelizing shell-to-shell compiler. Our formalization uncovered a critical bug where the original implementation did not handle configuration inputs correctly. Our new implementation also improves modularity, as transformations are now applied separately to the intermediate model. We will come back to the implementation, but let's switch to some results for now. Here we present the results of applying our transformations to 47 pipeline benchmarks. The x-axis shows the benchmark name, and the y-axis shows the execution time in seconds. Each pipeline benchmark corresponds to 3 bars. A green bar on the left showing the sequential execution time, an orange bar in the middle showing the execution time of the parallel configuration with only one optimization level enabled, that is covering only some of the transformations shown earlier, and then a blue bar on the right showing the execution time of the parallel configuration using the full set of the optimizing transformations enabled. The details of the differences between 2 and 3 are described in detail in the paper. All parallel bars are configured with a 16x parallelism degree, and speedups average 2.26 times and 6.16 times for the 2 optimization levels, respectively. Now, returning to the implementation, we want to emphasize that our work is open source. It is under continuous development with several contributors, and recently has been accepted as a Linux Foundation project, something that we're very excited about. More information about our work can be found on the paper and associated website. Thank you very much.
Hi everyone, I'm Taro at the National Institute of Informatics. I will present the joint work with Takesh at Chiba University. This is on a CPS transformation for implicit polymorphism. CPS transformation is a technique to transform programs into continuation passing style, in which control flow is exposed as continuations. For example, the right-hand side term is a CPS term, and K and the second argument to F represents continuations. CPS transformation has many applications. For example, it can establish the semantics of control operators like call CC and shift reset. And CPS is used as intermediate representations in compilers for functional programming languages, so CPS transformation is used in compilers to transform source terms to intermediate representations. A desired property of CPS transformation is type preservation, which means that well-typed source terms can be transformed to well-typed CPS terms. Type preservation is important to enhance the applications of CPS transformation. For example, it enables guiding type systems for control operators and verifying CPS compilers by typing intermediate representations and finally typing assembly code. Type preserving CPS transformation for polymorphic language was given by Haber and Lillebrecht on 1994, but their CPS transformations depend on the restriction that all polymorphic expressions in a source program must be values. So their CPS transformation can't be applied to implicitly polymorphic language without value restriction. Here, implicit polymorphism means programmers can omit type annotations. In other words, the existing CPS transformation can't handle polymorphic language with type inference if value restriction is not assumed. For example, OCaml supports type inference and employs a relaxed value restriction instead of simple value restriction. So CPS compiler of OCaml couldn't receive the benefits of type preservation to verify the compiler. Our long-term research question is whether we could obtain type-preserving CPS transformation for implicit polymorphism without depending on the value restriction. As a first step to answer these questions, we show that it is possible to define the type-preserving CPS transformation for the pure implicit polymorphic language. So more formally, we are working on the implicit version of System F, which is equivalent to the System F that allows this evaluation. So the body of type abstraction can be evaluated if it is not a value. So handling effectful languages is left for future work, but we find that obtaining type-preserving CPS transformations in implicit polymorphism is very challenging even for the pure language. To see the challenge, let me start with reviewing the CPS transformations for the Lambda calculus. A well-known definition of the CPS transformation provides a transformation rule for every term constructor as presented here. But for making the challenging easier to understand, I'm considering the factorized version of the CPS transformation. The factorized version consists of 3 stages. The first stage is to name intermediate computation results, and the second stage is to sequence computation by lifting redexes to the top of a program according to the evaluation order. Finally, the third stage makes continuations explicit. Problematic in implicit polymorphism is the second stage, so let's see the details of it. Redex lifting as the second stage can be expressed as a reduction on source terms, like this rule. Now I'm coloring the evaluation context that surrounds the redex by blue. So then we can find this rule lifts the redex to the top of the program and lowers the evaluation context into the function body of the redex. This rule characterizes a part of CPS transformation. So this rule must be type preserving for the CPS transformation to be the type preserving. But we find that it is not in implicit polymorphism due to the existence of evaluation context such that the whole appears under the type variable binder. So to see it, let's consider regex routing instantiated by such an evaluation context, like this. Here, the whole appears under the binder. Then we could obtain this reduction. On the left-hand side, the argument type tau and the argument term e2 may refer to type variable alpha. However, on the right-hand side, tau and e2 can't refer to alpha, because they are placed outside the scope of alpha. So this is not type preserving, and so naive definition of CPS transformation for implicit polymorphism is not type preserving either. We can view the root cause of these problems is in the conflict between two roles of type abstraction, generalization and binding of type variables. For generalization, the evaluation context E' requires the whole to be filled with a term of a polymorphic type, because the type of the regex is generalized by the type abstractions on the left-hand side. So the type abstraction must be lowered into the function body on the right-hand side. But to bind alpha in tau and E2, we need to lift the type abstraction together with the regex. So in summary, the type abstraction must be lowered for generalization and must be lifted for binding. This is the reason why the regex routing is not type preserving in implicit polymorphism. A key idea to solve this conflict is to decompose type abstractions into two constructors, restrictions and open type abstractions, according to the role of type abstraction. So restrictions are new constructor for binding, and they don't do generalization. By contrast, open type abstractions are introduced for generalization, so they don't do binding. The separation of binding and generalizations using these two constructors can be found in their typing rules presented here. So the typing rule for restrictions introduces a new type variable alpha, but it doesn't require the entire type to be polymorphic. By contrast, the typing rule for open type abstractions doesn't introduce any type variables. Instead, it requires the generalized type variable alpha to be in a context. And then it assigns a polymorphic type obtained by generalizing alpha to an open type abstraction. So we can find the restrictions only bind and open type abstractions only generalize type variables. But these two constructors just separate two roles of type abstractions. So the ordinary type abstraction can be expressed by combining restrictions and open type abstractions. So in this encoding, the restrictions first introduces a type variable alpha, then open type abstraction generalizes it to assign the polymorphic type. To find the usage of these new constructors, let's see three examples of typing judgment with them. For the first example, this combination of restrictions and open type abstractions expresses the ordinary type abstraction, so it can be of the polymorphic identity type. The second example is not well typed because open type abstractions requires the generalized type variable alpha to be in a context. Perhaps the third example is the most interesting. It shows that open type abstractions can generalize the type variable alpha, which appears in the type of x, although x is bound outside the open type abstraction. This is impossible if we use the ordinary type abstraction instead of open type abstractions. But open type abstraction can generalize alpha, and it can be of the polymorphic identity type. Okay, let's see how the new constructor solves the problem with regex lifting in implicit polymorphism. As presented before, type abstractions can be expressed by the combination of restrictions and open type abstractions, so I'm considering this term as a target of reductions now. Then the regex lifting in this setting is performed by two steps. The first step is to lift the restriction constructor new under the evaluation context E prime. The second step is to lift the regex. And in other words, the blue card evaluation context, including the open type abstraction, is lowered. We can find the resulting term is well typed because the requirement on generalization is satisfied by lowering the open type abstractions, and the requirement on binding is satisfied by lifting the restriction. So separating generalizations and binding features of type abstractions enables type-preserving regex lifting. Following this idea, we could define type-preserving CPS transformation from implicit system F to system F enriched with restrictions and open type abstractions. But this architecture still has a problem, which is that unrestricted use of open type abstractions is not type safe. This unsafety comes from the regeneralizations of type variables. So this term M is a counterexample to type safety. By ignoring the restrictions and open type abstractions, we can find it takes the two arguments x and y, and it returns the first argument x. So this example M includes the two open type abstractions for alpha, and it is assigned this polymorphic type. So the type system tells us M returns the second argument, but running free applied M would return the first argument. So it means that unsoundness of the type system. The root cause of this unsafety is in regeneralization of type variable alpha. In general, we need to enforce the same type variables is generalized at most once. So to enforce it, we use affine typing, but this talk skips the details of using affine typing. So please see our paper for detail. Then we designed a new CPS target language, Big Lambda Open, which is a system F enriched with restrictions, open type abstractions, and affine typing. And we also provided a type-preserving CPS transformation from implicit system F to Big Lambda Open. So we use the fact that the implicit system F uses continuations only linearly to show that the type variables in CPS terms are generalized only once. And the topics in the paper include the details of our CPS target language and the CPS transformation. And we also show that the CPS transformation is meaning preserving. And we also prove the CPS target language satisfies the parametricity. A key message of this work is that it is very challenging to obtain type-preserving CPS transformations for implicit polymorphism without depending on the value restriction. As a first step, this work addresses the implicit version of the system F, but there are many programming features not handled in this work. For example, it is interesting to support effects. Thank you for attention.
Hi everybody, my name is Dougal. It's like Google with a D, and I'm really excited to be here. It's my first ICFP. My background actually is physics and later machine learning, and so as a result of that I spent a lot of time writing in MATLAB. And it's easy from a modern PL perspective to look down on MATLAB and NumPy. They do seem so backward. But I actually don't think we've come up with a viable alternative yet, and it's kind of on us as the PL and compilers community to do that. The good news is, though, I think we're getting pretty close, and in this talk I want to describe what I think still some of the outstanding problems are and the progress that we've been trying to make towards this in this experimental language called DEX. The idea of the MATLAB model is you have a flexible, dynamically typed host language like MATLAB or Python, and you use it to string together a fixed set of high-performance kernels. And this can work really well, actually. First, it gives you easy access to hardware accelerators like GPUs and TPUs. You can have the best CUDA programmer in the world implement a superfast matmul, and if that's where your flops are, then you're going to go as fast as the hardware can possibly go. It also plays really well with automatic differentiation, or AD. What's nice about these primitive sets that you tend to see is that they're closed under differentiation. For example, the derivative of matmul is also a matmul. So the parallelism and performance that you had in the original program translates perfectly over to the derivative program. And this is in contrast to traditional imperative AD in Fortran and C, where getting parallel derivatives is still an active research area. This also turns out to be surprisingly hard to get right in functional array languages, for example, DEX. And so I'll have more to say about this a bit later. Now, another important strength of the MATLAB model is that it works really well as an embedded DSL in an existing host language. So there's no need to design your own language from scratch and build an entire compiler for it. But we're all programming languages enthusiasts, and we actually love doing that kind of stuff. So I'm actually going to move this over to the bad column. Now, there's another interesting feature of the MATLAB model, which is that you often end up with really terse code because of this feature called rank polymorphism. I think it comes from APL. The idea is that each of your built-in operators comes with its own map. So if you want to, say, apply a matrix multiplication to several matrices at once, you can do that with a single call to the matmul operator, and you just give it a high dimensional argument and it maps over all of the subarrays. This is going to be a controversial opinion, but I actually see rank polymorphism as more of a bug than a feature. You're forced to have it in an implementation of the MATLAB model because it's the only way to express a map. You don't have a map combinator at the top level. But it actually forces users to organize code in an unnatural way. You have to carry around batch dimensions everywhere. You've got to push all your loops to the inside. I agree that it is nice to be able to add two vectors with the same operation that you use to add two scalars or two matrices, but an ordinary type class system handles that perfectly. Now, moving on to the con column, we've already talked about rank polymorphism, shape errors, indexing errors. These are a huge pain point in MATLAB programming. We'd love to have a type system to catch these. And actually, more than that, we'd love to be able to have a type system to help us reason about them and document them. If you look at MATLAB or NumPy code, it's always full of comments describing the shapes of different variables, and these things should just be type annotations. It's a no-brainer. But the big one really is about expressiveness. In a proper higher-order array combinator language, you at least expect to be able to do map, reduce, and some kind of sequential scan or fold. In the MATLAB model, you get map only via rank polymorphism, and we've discussed the limitations there. You get reduce through some small set of reduction operators like summation and product, and you get sequential scan only by falling back to the host language, and in that case you face a massive performance cliff. So can we have the good parts of the MATLAB model without the bad? That's really been the goal of DEX. We wanted a language that was easy to compile to GPU, has AD built in, and then also has a static type system for shape and indexing errors. I think the easiest thing to do now is just to show you what it looks like so far. So on the right, I just have Emacs, and on the left, just going to start up the DEX notebook. And what this is going to do is it's going to watch the file for changes and run it every time it changes. To give you a flavor of the syntax, let's just abstract this into a function. Okay, so far everything looks like an ordinary functional language. After Hello World, the next conventional program is factorial, so let's try that. Well, that failed, and the reason is that DEX doesn't have recursion, doesn't have recursive functions, doesn't have recursive ADTs. Functional programming traditionally is built around recursion, and so how do we do anything interesting without it? The answer is that we use iteration instead of recursion, and we use arrays instead of recursive ADTs. So let's take a look at how arrays work in DEX. We saw an example before of an array literal, so let's make one of those. We can print it out and we can query its type. So here's the first time we see something a little bit different. This array has a type that looks a bit like a function, but instead of an ordinary single arrow, we have this double arrow. And what this is saying is that an array is really a mapping from the index set. In this case, the index set is fin4, finite 4, the set of elements 0, 1, 2, and 3, to integers. And actually, this analogy between arrays and functions, we carry it all the way through. So, for example, a higher dimensional array, if we made this a nested array, we see it's just like a binary function, in fact, a curried binary function. And of course, we could also have the uncurried form. So let's explore this analogy even further. So now let's take a closer look at functions, which is something we're very familiar with. One thing I've learned is that PL is a lot like quantum field theory, in that everything is described in terms of creation and annihilation operators, or introduction and elimination forms. And so for functions, we have the introduction form, which is lambda, and we have the elimination form, which is function application, and we have the function type. And we can make the same sorts of things for arrays. So we can now ask, what are the corresponding forms for arrays or tables? We've already seen the type of arrays, which is completely analogous to the type of function, just the index set type and the element type. The elimination form is clearly just indexing. But what about the analog of lambda? Reasoning completely by analogy, we can just create one. So we'll call it for. So for I, and then somebody. This sort of thing is sometimes called build in array combinator languages, but the idea is that this constructs an array whose elements are the result of evaluating the body of the expression at each of the valid indices. And when I say valid indices, that already highlights one important difference between functions and arrays, and that's that the domain of arrays, the index set, really has to be a finite thing that you can enumerate exhaustively so that you can build an array. So the array type is actually constrained index to have an index set type class associated with it, which means that it's finite and enumerable. Now, one thing about working with functions that we're familiar with as functional programmers is there's often two styles of working with functions. There's the pointful style and the point-free style. So to illustrate these, let's see some examples. If we wanted to flip the order of arguments of a function, the point-free style would just be to use a higher order function. There's one called flip. Whereas the point-full style is to use an explicit lambda and explicit binders and variables. And we can actually do exactly the same thing with arrays, of course. In the case of arrays, the analog of flipping the arguments of a function is swapping the indices of an array, so transposing the array. So let's call it transpose. The title of my paper was a pun on getting to the point. And in some ways, the point of DEX is that it's often quite natural to write array programs in this pointful style, whereas the traditional MATLAB APL style of array programming doesn't really give you access to it. The only way to transpose an array is to use a built-in function called transpose. So it's as if you were being asked to do functional programming and you had to do it entirely in point-free style. Point-free style can be a very appropriate choice in many situations, but of course you'd rather have both point-free and pointful styles available to you, so you can use whichever is appropriate at the moment. So now let's actually implement these for real, just to see them working. So we can print the types and values, and we can see it works just like you'd expect. Here I wrote the types on the binders and for very explicitly, but just as with Lambda, if they're obvious enough for the context, it's perfectly acceptable to leave them out. Let me also take this opportunity to show what sort of type error you get if you get the indexing wrong. So let's imagine we wrote this type signature for transpose, but we wrote x.jj instead of xji. This is the error you get. It's a completely static error. We haven't actually applied transpose to anything yet. This is just when you've defined the function. And I'd argue that's a pretty reasonable error. Let's take a look at how you might sum over different axes of this two-dimensional array in this pointful style. So if you wanted to sum the columns together, and if you wanted to sum the rows, then of course you would do it the other way around. But what if you wanted to sum all of the elements in the array? One thing about the approach in DEX is that we're quite flexible in what we consider an index set. So these fin n index sets are index sets, but you can also have things like tuples of index sets. Anything that can plausibly implement the index set type class is a valid index set. So in this case, what we can do is we can write sum of for ij as a tuple sum data.i.j. And you see that sums all the elements. If you ask for the type of this thing, it's essentially the array analog of an uncurried function. Instead of being a nested array, it's a single flat one-dimensional array whose indices happen to be pairs of indices. So this index polymorphism lets you play a lot of fun games. You can imagine going further and having index sets that are sum types, or even index sets that are tables, which give you exponentially sized arrays. And there's all sorts of crazy things that people are playing with there. Now, I still haven't explained how we survive without recursion. Remember, we at least want to be able to do reduction and sequential iteration, and so far it only looks like we can do map with this for construct. One approach would be to add a bunch more combinators, and that's the second-order array combinator approach. Instead, what we're going to do is we're going to add side effects to the language, but we're going to make sure that our side effects are very explicit in the type system so that the compiler can reason about them. So let's take a look again at the array function analogy. Our effect system is roughly based on Coker's, so function application can produce effects, and function definition, Lambda, doesn't produce effects. It's pure. With arrays, though, the situation is the exact opposite. So indexing is cheap and pure, but array building, this for expression, it's expensive, potentially, because it builds an array, but also it can have side effects. It sequences effects. So this for is actually looking less like a map, and it's more like mapm or traverse. It has sequential semantics, but the compiler can still parallelize it if it can prove that it will generate the same result. So to do reduction, we just need some sort of writer effect, or we call it actually the accumulator effect. And if it's associative and the compiler knows about it, then we can still parallelize it. To do sequential iterations, we just use a state effect. Now finally, I want to go back to the problem that I alluded to at the very beginning of the talk, which is this tricky issue about AD and functional array languages. So here's the problem. The fundamental promise you're supposed to make in an AD system is that the derivative program should only cost a constant factor more than the original program. But array indexing seems to violate this. Indexing itself we expect to be an O of 1 operation, but the transpose of indexing takes a scalar and produces a one-hot array full of zeros, and that seems to be an O of n operation. You can imagine trying to get around this with compiler optimizations that turn one-hot arrays into in-place updates, but I've never seen a convincing solution that really guarantees you the right asymptotics. The embarrassing thing is that imperative languages seem to have an edge on us here. In an imperative language, you just emit a mutating update for the backward pass, and you get the right asymptotics. So in DEX, we manage to get the best of both worlds. We have the right asymptotics, and we preserve parallelism. And we do this just using the writer effect. So we do emit mutating updates in a sense, but they're monoidal associative accumulator updates, and so they don't actually interrupt parallelism. The accumulator effect really hits this nice sweet spot where it's sort of more machine-oriented than pure functional constructs, but it's still more algebraic than a straight-up imperative program. So you get in-place updates without sacrificing parallelism. So that's it from me. Thank you so much for watching, and I'll see you in questions.
everyone, I am Pedro, and I'm here to talk on how to integrate shared state into prepositions as types. This is joint work with Luís Caix. We start with shared state, which is everywhere. It's the backbone of imperative programming languages, such as Java, but also functional programming languages, such as Haskell, offer support for shared state. However, despite its ubiquity, safely programming with state, aliasing, and concurrency is considered to be quite a challenge. There is therefore an effort to find tools that in some way or another try to discipline the usage of shared state. The other half of the title concerns prepositions as types, which is a bridge between logic and computation that allows knowledge to be transferred between these two fields. Under this bridge or correspondence, logical prepositions are connected to types of a typed programming language, logical proofs to programs, and proof simplification to program evaluation. Prepositions as types is a notion that is quite well established for the functional core of programming languages, for example, the simply typed Lambda calculus and System F. And a decade ago, it was extended to concurrent programming languages by connecting linear logic to session types. However, it seems that shared state does not fit into prepositions as types. One of the main challenges is to reconciliate the two seemingly opposite notions of program behavior and proof simplification. Because on one end, we have non-deterministic behavior that emerges of racy concurrent programs that manipulate shared state. And on the other end, we have a confluent notion of proof simplification, which is required by prepositions as types. Furthermore, with the presence of high-order store, we can potentially express non-terminating programs, such as the landings not, which compromises the existence of proof normal forms, another requirement by prepositions as types. Our proposed solution to accommodate shared state into a prepositions as type framework is PySS, a session type process calculus with first-class reference cells. PySS is a session-based concurrent programming language. Several interactions occur at the same time, and they occur always on matching dual pairs. Furthermore, interactions are structured around the notion of session types, which are dynamic entities that prescribe a communication protocol describing which and when interactions take place. At a logical level, PySS is a conservative extension of the session-based interpretation of classic linear logic, which results from the addition of two duality-related modalities, box why not, which types reference cells, and box bang, which types cell usages. The logical principles associated with these two modalities are inspired by differential linear logic. In PySS, typing judgments have this form. There is a process P on the left and a typing context on the right. And the typing context is a partial finite assignment from session names to types. On understanding typing contexts, it might help you to picture the process P as a black box, with a collection of wires X and Y's, whose endpoints satisfy a certain protocol, specified by the A's and B's. Our typing judgments are dyadic, which means that the typing context is separated into two parts, a linear, denoted by delta, and the unrestricted, which absorbs weakening and contraction and is denoted by gamma. Channels on the linear side cannot be copied nor discarded, whereas channels on the unrestricted side can. The basic rule of our type system is the logical cut rule, which is interpreted by interactive composition. This defines two processes, P and Q, that run concurrently, interacting on a single private linear session X. Process P provides a behavior of type A along session X, whereas Q offers on X a dual behavior of type dual A. We annotate the cut with the offering type of its left argument. We now turn our attention to the typing rules involving shared mutable state. We start with a typing rule that introduces the box why not modality and which is computationally interpreted by a process that defines a reference cell available on C and which stores a persistent session V. The behavior at V is defined by a replicated process P. Logically, the rule corresponds to box why not dereliction, I would like to call your attention to the fact that the replicated process P does not depend on free linear names, as you can see on the premise of the typing rule. Particularly, it cannot depend on free cell references, so our language cannot express circular data structures, such as the landings knot. However, a replicated value stored in a cell may of course allocate and use reference cells locally. We now turn to operations on reference cells. We start with the free operation, which introduces the box bang modality and is interpreted by a thread that releases its cell usage C and continues as Q. In fact, observe that the cell usage C is no longer accessible by the continuation Q. Logically, this rule corresponds to box bang co-weakening. When a cell is not shared by any other thread, free will cause the cell to be deallocated. The other two cell operations are read and write, which are atomic operations. Read accesses the contents of cell C, which are copied and received by the continuation Q at parameter V. The write operation destructively updates the contents of cell C with a session V implemented by process Q1. Then the writing process continues as Q2. Even though the cell changes its contents, the update is not strung, and so the cell protocol is left unchanged. Logically, these typing rules incorporate box bang called the reliction. We will now illustrate the sequential cell operations with a short example. Consider the following system, in which a reference cell at session C is initialized with a persistent Boolean value true, the cell being typed by box why-not bool. The cell is composed by cut, with a process that first reads the cell on input parameter X, then writes the Boolean false, frees the cell usage, and continues as P. After the read interaction, a persistent copy of the Boolean true is spawned on X and composed by cut with the client continuation. After the write interaction, the cell contents are updated from true to false. Since the cell is not being shared by any other thread, the free operation will cause the cell to be deallocated. Notice that up to this point, all cell usages are handled linearly, which means that they cannot be implicitly discarded nor copied. Releasing a cell is explicitly indicated by the free operation. However, since there is no point in having mutable state if you cannot share it, we also have a sharing operation. Sharing is introduced by this typing rule, in which a cell usage C is being shared between concurrent threads P and Q. Logically, the share typing rule corresponds precisely to differential linear logic box bang co-contraction. Co-contraction enforces that two concurrent threads share a single cell usage. This is related with the basic acyclicity of linear logic proofs, where in a cut, two threads interact only on a single session. This property is key to ensure deadlock freedom of our typed calculus by purely logical means. Notice, however, that a single shared cell may group all the states shared by the two threads, as in a resource bundle, and the reference cell can be used by any number of client threads by iterated use of the share construct. Other property that I would like to highlight is that sharing in PySS is dynamic, in the sense that the number of clients sharing a common cell usage can grow unbounded and shrink as computation takes place. This contrasts with some session-type languages in which the number of participants sharing a session is statically bounded by the type system. We will now illustrate how this concurrent system executes. A memory cell is being shared between two threads. One thread writes the Boolean true and continues as P1, whereas the other writes false and continues as P2. First, the system is expanded into a non-deterministic sum, in which the two concurrent write operations are interleaved and brought to evidence, using the fundamental law which relates concurrency with non-determinism. Further laws allows the cut to be distributed over sum. Reductions on its summand are now independent, and after the four write operations, we obtain a non-deterministic sum of two cells, whose state depends on the last write operation that took place. A sum process represents a non-deterministic choice between two alternatives, each offering the same typing context. Sums are also present in differential linear logic, where cut elimination needs to generate sums of proofs. Sums internalize non-determinism, allowing us to define a confluent proof simplification. In our model, sums satisfy the expected axioms of non-deterministic sums of process algebras, like commutativity, associativity, and idempotency, remarkably modeled as logical proof conversions. We extend PySS with locking primitives, obtaining what we called PySSL. To the collection of types, we add a pair of dual modalities called locked box why not and locked box bank, which represent locked state and act as a mirror of the basic cell modalities, which in turn represent unlocked state. Then we have locking and unlocking operations that essentially alternate between the two states. Other flavors of co-contraction ensure at the type level that only one single thread may be interacting with a locked memory cell, thereby allowing us to define critical sections. Remarkably, the linear logic type chiplin preserves the deadlock freedom property, where typing ensures a cyclicity in communication, herein in locking. Concerning the method theory, we have formalized the reduction-based operational semantics of PySSL, which is comprised of a structural congruence relation that captures the static laws and a reduction relation that captures the dynamics of our calculus. As a consequence of our proof-theoretic approach, our language enjoys type preservation and deadlock freedom. Since we internalize non-determinism with sums, our calculus enjoys confluence. Therefore, proof reductions and conversions represent proof identities or behavioral equivalences. Finally, we also establish a normalization result by applying a structural cut elimination technique to our calculus. All the detailed proofs can be consulted in the extended technical report. We developed the type checker and an interpreter, which were submitted as a companion artifact for the paper. Both the type checker and the interpreter were written in the Java programming language. We used the Java CC parser generator, and we have made extensive use of the Java util concurrent package to implement the fine-grained concurrent runtime system. Some details of our implementation worth mentioning is that we have committed non-determinism in our interpreter, so that the sum operator is not present in our practical runtime system. The share construct is simply implemented by object aliasing, and in order to reduce the overhead associated with thread creation and destruction, we have opted to manage the execution of concurrent tasks for a catched thread pool. All the examples in the paper are validated by the implementation, and we also have developed many others, ranging from the definition of inductive data types, such as naturals and lists, to concurrent shareable ADTs, such as canters, stacks, and queues. These examples illustrate how the presence of standard, essential, and universal type quantifiers harmoniously combine with the basic stateful framework of PySSL. I would like to point out that when running complex examples, our implementation spans thousands of short-lived threads, which synchronize perfectly, such is the power of session types and linear logic. Our development was based on the session-based interpretations of linear logic. On the proof-theoretical side, we draw inspiration from DIL. The works on manifest sharing were the first proposal to represent shared state on top of prepositions as types, and then were followed by a series of recent works. To conclude, we defined PySS, a session-type process calculus with first-class reference cells. We showed PySS enjoys the basic properties of prepositions as types, as justified by key method-theoretical results. We develop an extension PySSL that allows critical sections to be defined. We develop a type checker and an interpreter, which was submitted as an artifact, alongside with several examples that showcase the language expressiveness. As future work, we like to investigate how to handle linear state and explore how dependent types may express resource invariants. Thank you, and I am willing to take any questions.
Hi everyone, I am Chaitanya Koparkar, and today I'm going to talk about this compilation technique that combines the benefits of serialized data representations and parallelism to optimize programs. So let me start with data representations. As you can see, the ways to represent heap memory can be arranged to form a spectrum like this, where each point has a different performance characteristic. On one end, we have the fully pointer-based heap, in which memory is allocated for every object when it is needed, and then these objects are tied together using pointers. Almost all programming languages use heaps like these because this layout is really uniform, and it's also easy to manipulate data on this heap. But for certain kinds of programs, particularly those that process large amounts of data, all of these pointers can add a lot of overhead. On the other end, we have the fully serialized heap, in which there are no pointers and all data is allocated in a single memory buffer. And in this heap, the updates are slow, but the traversals are really efficient because this representation has really good data locality. And there are also various other choices that we can make. So we can serialize some parts of the heap, but then we can allow pointers in some other parts and so on. And previously, the only way to get a serialized representation was by writing low-level C code. But in past work, our group has developed this compiler called Gibbon, which makes this a language feature instead of something that you have to do by hand. So Gibbon takes programs written in a subset of Haskell, and it compiles them to use serialized heaps automatically. And it gives good performance. So here's a table which shows the runtime performance of programs compiled using these three compilers relative to Gibbon. And Gibbon is 2 to 3 times faster than any of them for sequential performance. But it turns out that it's not just sequential performance. Serialized representations are really good for parallelism as well. And that's the main topic of this paper. So we show that not only can Gibbon provide parallelism, but for many programs, it actually scales better than existing systems. And here are the numbers for that. So Gibbon is 4 times faster than GHC for parallel programs. So not only do we get normal parallel speedup, but we actually get better parallel speedup over our already better performance. So it's not just that Gibbon scales better than GHC, but it was already faster than GHC, and then it scales better. In this paper, we show how you can take advantage of this serialized representation to get this efficient parallelism. And the main challenge that we have to solve there is in a serialized representation, you can only read and write values in a fixed order, unlike in a pointer-based representation. So for example, in a pointer-based heap, if you're at a node n, and if you want to process both of its subtrees in parallel, then it's really easy to do so because you can instantly access both of them. But this is not really possible in a serialized representation because you don't know where the right subtree has been allocated to because you don't know how big the left subtree is. So the only way to get to a particular field is by walking over all of the fields serialized before it, and then this loses all parallelism. For allocations, if you want to allocate both of these subtrees in parallel and also keep the resulting value fully serialized, you won't be able to do so because you won't know where to start allocating the right subtree because you don't know how big the left subtree is going to be. So in order to enable parallelism, we'll actually have to reintroduce some pointers in this representation and then deal with the problems that that might cause. But before I get to that, let me present some background information on serialized data. So now we are going to talk about what serialized data looks like and how Gibbon takes programs written in Haskell and turns them into programs that operate on serialized data. And the way Gibbon manages serialized data is by using this IR language called the location calculus, or local in short. In local, the heap layout is configurable at the level of a data type. By default, all data types are going to be fully serialized, but you can also specify that you want to include pointers in certain places. And we'll see why we need this sort of thing later on. But first, let's look at local in a bit more detail. So regions and locations are the most important features of local. Regions are sort of like unbounded memory buffers, which are used to allocate all data. But each region only contains a single data structure. Then these locations are precise positions inside a region. So here A is the location of the root of the tree, B is the location of the left subtree, and C is the location of the right subtree. These locations are very similar to pointers in Z, but the main difference is that you can't do arbitrary pointer arithmetic with them, and locations can be written to just once. To introduce regions, you use a standard let region form. And then there are a handful of different ways in which locations can be initialized, and you can relate them back to regions. So A is at the start of this region, B is one past A, and C is after every cell occupied by this tree that is rooted at location B. And by only allowing you to initialize locations in a limited way like this, Local is able to establish certain invariants which ensure that the values being constructed are correct. Finally, you can allocate data on the heap by using a data constructor. In addition to the regular arguments, constructors also accept a location argument, and then they write the data at that location. To make all of this a bit more concrete, let's walk through an example that constructs a small binary tree. And we're going to use a call by value execution model, just like the formal semantics. So we start this program by creating a region to store all of this data. Then we bind a location at the start of this region. And then we bind a location right after this. And we create our first subtree at this location B. Then we want a location right after this leaf. And we allocate our right subtree at this location C. And once both of these subtrees have been allocated, we can finally construct the node which writes this tag n. And this tag has to be written at the end to establish certain invariants of the formalism, but it's okay for us to ignore these details for now. And actually, the implementation tries to perform these writes in order because it's more efficient to do so. And here's a little picture which shows how reads and writes work in local. So each region has a single allocation pointer, which always points to the next available cell on the heap. So it starts at the beginning of the region, and each write moves it by one, and this is how it moves along the length of the region. And reads work in a similar way as well. So far we have seen what local is and how sequential local programs run, and now let's see how to parallelize it. So the first thing to observe is that reads and writes which target separate regions are naturally parallel. Each region has its own allocation pointer and its own read pointer, and it's easy for us to use these in parallel. Parallelism within a region is also safe since local is a pure language, but this parallelism is difficult to get to. But in most local programs, a single region often contains large amounts of data, and it's important for us to get to this parallelism as well. And we saw this problem earlier where not knowing the size of the left subtree stopped us from being able to read or write this whole tree in parallel. So now let's see how we can fix that. For parallel reads, we introduce offset pointers like this. This pointer points to the right subtree here, and we can access the right subtree directly using this pointer. For the left subtree, we know that it's going to be serialized right after this pointer, and now we can process both of these trees in parallel. For parallel allocations, we actually allocate both subtrees to separate regions, and then we tie these regions with a pointer like this so that a subsequent traversal can process them properly. And if you're wondering that this might cause fragmentation, I'm going to show you how we control that in a little bit. But first, let's look at this allocation idea in a bit more detail. So here's our program from earlier, but this time we have marked the first let bound expression with a spawn primitive. And this indicates parallel execution. So we are going to spawn a task to evaluate this bound expression. And when its value gets demanded later on, we will synchronize with that task. So let's start this program. And the first three steps actually run exactly like before. And we reach the fork point at the next step. So here we create a task to evaluate the bound expression. And the body expression keeps executing in the parent task. Now, suppose that the parent task takes a step and it reaches this after expression that is trying to get after this leaf that's still being constructed in parallel. So we can't evaluate this after expression directly because we don't know how big this value is going to be. And we also don't want to synchronize with this task, because if we do that, then we will essentially sequentialize this whole program. And we don't want to do that. So the way we avoid it is by creating a fresh region whenever the program reaches such an after expression that's trying to get after a value under construction. And now we essentially have two allocation pointers, and both of these allocations can run in parallel just fine. When we reach this join point, we then synchronize with this task. And now we know that both of the subtrees have been allocated. But since they've been allocated to different regions, we tie these regions with a pointer like this. And then finally, we can construct the node. And this is the main idea behind parallel allocations in local. So now let's talk about fragmentation a little bit. Observe that we create fresh regions and introduce pointers to enable parallelism. So you might be wondering that how is this really different from a pointer-based heap? And that's fair. If we create too many fresh regions, we will actually go back to a pointer-based heap, and then we lose all benefits of serialization. So that's why our implementation creates fresh regions only when they're really required. And the first control we provide is primitives to control the granularity of parallelism. By controlling that, you automatically restrict the number of fresh regions to the number of tasks that are spawned by a program. But actually, this alone isn't sufficient, because not all tasks which are spawned will actually run in parallel. So we create fresh regions only when real parallelism is created. And we detect that by detecting a steal in the Silk work stealing scheduler that we use. And by using both of these controls, we are able to restrict the fragmentation level to a minimum. We actually did some experiments to measure this fragmentation. And the first thing we measured is the number of fresh regions that get created specifically for parallel allocations. And we observed that this number is very small, up to 0.1% of all of the objects that are created for allocating fully pointer-based values. So the values that we allocate are still mostly serialized. Then the next thing we measured is the downstream effect of fragmentation. So all of these traversals that operate on fragmented values, we would expect them to get a little slower, since they now have to traverse all of these additional pointers. But we observed around a 5% overhead for such traversals compared to a traversal that operates on a fully serialized value, which was allocated sequentially and has no fragmentation. And even with this overhead, this traversal is still much faster than traversing a fully pointer-based value. And with all of this, we get the performance numbers we saw earlier. So to wrap up, I talked about what serialized heaps are and showed you that they can be efficient for sequential and for parallel computations. But I've only touched upon the main ideas here, and the paper actually has a lot more details about the formalism and also about the experimental evaluation. So please take a look at that for more details. And with that, I end my talk. Thank you for listening, and I look forward to your questions.